Hey there, Himanshu this side, physics faculty at AskIITians. So welcome to the lecture number 2 of gravitation. And in this particular session, we are going to talk about the one of the beautiful topic and the most favorite topic among the students of grade 9, which is the gravity. So in the previous section, I hope you have watched the video. In the previous lecture, we have talked about the gravitational force, right? And we have understood that how beautiful it is. Whenever we have two mass objects, they always attract each other. So that was the concept of gravitational force, which was completely new for we guys, right? It is an intrinsic property of material bodies that they will always attract each other, and which is making the planets to revolve in a certain orbit, which is making the satellites to go in a certain orbital path. So it's a very wonderful phenomena, right? Now, once we understand that what is gravitational force, so in the previous lecture we have talked about the gravitational law, the universal law of gravitation. What does it says? Yeah. So we learned that F is equals to G m1 m2 divided by r square, and that capital G we have used there. That capital G is called the universal law of constant of gravitation. Now this capital G value never changes. Either you are on the surface of Mars, or you are on the surface of Venus, or you are on the surface of Earth. The capital G value would be same. Now, there is another thing, some phenomena which are related to the law of gravitation. Now, if there is a gravitational force which exists here, so now what is the phenomena which are related with this? What does it causes? Right? How does it make the planets to go in a particular path? Or if I come to a very simple question, when we throw an object vertically upwards, why does it come down? So reason behind that is the gravitational force. Now in the chapter number 1, which is the motion, you guys have learned that when a body is thrown upwards, then it will come down, and we use the acceleration as equal to small g. So what does it mean? From where does it come exactly, that small g value? That thing we are going to discuss in today's lecture. It is going to be a very interesting lecture, so please watch the video till the end if you want to understand what is exactly small g. And also, after this lecture, you should also make a note that small g and capital G are two different things, because that's a very basic confusion among the students, that small g and capital G, they think that they are same. Capital G was the constant of gravitational force. It is always same. But small g value would not be always same. Why it would not be same? So let us begin with this lecture now. So now I am going to present you the slides. Okay. So here we can see that the gravitation lecture number 2 we are starting. So today, what all topics we are going to cover? Free fall motion and the value of acceleration due to gravity. And later on we will discuss what is the variation in value of g due to height and depth, whether it will change or not. First of all, we will understand that the small g value. So let us begin now so that you can understand what is small g. So, okay, I'm starting now. First of all, the concept of gravitational field intensity. Now, this gravitational field intensity is the same thing, which you have been knowing it by the symbol small g. And you have all have been using the value 9.8 meters per second square on the surface of Earth. So, how does it come exactly? That's what I will be explaining you in this particular session. Okay, so imagine you have a mass capital M. That's a mass capital M. And now you have put a small m mass here. We know that the total force which will be experienced by this small m mass due to the capital M mass would be how much? It will be equal to capital G, small m, capital M, divide by the distance between them. And the distance between them is r squared. So that's the gravitational force acting between the two bodies, right? Okay. So now here we can see that there are two bodies. One is capital M, another is small m. And the force experienced by the small m mass due to the capital M is how much? G capital M small m by r square. Let me write it in a different way. I can write small m separately here. Now why I'm doing this, you will understand this very soon. Okay. So when the small m mass was there, the force experienced by it was this much. Now see guys, what actually happens if you keep a capital M mass? Now this capital M mass can exert a force on other particles. If you keep something around it, it would be definitely exerting a force on the other mass particles. I hope you got my point, because that's the gravitational law says, the universal law of gravitation. Every body would exert a force on another bodies. Right. So if you keep a capital M mass body here, now up to what distance it can exert a force? Let me take one analogy. Suppose this is your home, all right, and now you have a very good hold over this area. Everybody knows you, right? So if you have a fight, then easily you can handle the fight in this area, in this particular area. But what will happen if you had a fight not in this area but out of this area? Suppose you had a fight with someone in this area, then this is not your area now. All right, so you would be scared, exactly, because you do not have any influence over there. Your influence is up to this area only, the red color part. Got my point? So this red color region is called the field of yours. Like this is your field actually. You can exert a force on any other body. I hope you're getting my like you're getting my point. What do I mean by force here? Right. So this is your area basically. You can exert a force on someone if somebody is in this area. But if somebody is out of this area, you won't be able to exert a force on them. Similarly, when we talk about a mass particle, then this capital M would also have a field around it, up to which it can exert a force. So gravitational field, that is what we call. So that's the meaning of gravitational field. That due to a mass particle, up to what distances it can exert a force on other body. Up to what distances it can influence the other body. The region is called the gravitational field. Similarly, you can take example of a cricket playground. Now, fielders can set themselves anywhere in this playground. All right. Now, a fielder cannot go out of this playground because that is not his field. Yeah, exactly. So that is what do you mean by the field? The area in which you have the influence. So similarly, we will talk about the capital M mass body. In which area, in what region, this capital M mass would have the influence. That is what we will call as the field. And now when you calculate the intensity of this field, how strong is that field? How strong influence you have in that area? How strong influence you have that in that region? That is what we call the gravitational field intensity. All right. So that's the meaning of gravitational field intensity. So if I talk about a capital M mass body, I hope you understood this analogy. Now I'm going to apply the same analogy for the mass particles. Now if I talk about the mass particles, so what we can do, see, due to this capital M mass, the force which will be exerted on small m mass will be G capital M small m by R square. So on small m mass, the force which was exerted is Gm over R square multiplied small m. On a m kg mass, m I am referring to the small m. So on a small m kg mass, the force which is exerted by the capital M is Gm small m by R square. If I would have taken unit mass, right? If I would have taken unit mass, then what is the force? Gm by R square. So for a unit kg mass, it's just a unitary method. In one rupee you get 10 books, let's say, right? So in 1 rupee you get 10 books. So in how many books you will be getting in 10 rupees? So for 1 rupee you get 10 books. So how many books you will be getting for 10 rupees? So that would be given by 10 multiplied 10, 100 books. Simple. Exactly. For a unit kg mass, the force exerted by capital M is Gm by R square. This Gm by R square is called the intensity. Ig, small g I am using in the subscript. I, then in the subscript, small g. So basically, what is gravitational field intensity? Force exerted per unit mass. force exerted per unit mass is called what? This is called the gravitational field intensity. So that is the simple meaning of gravitational field intensity, force exerted per unit mass. So now if you know the gravitational field intensity, then I will represent it by Ig is equals to Gm over r square. So basically due to the capital M, what is the gravitational field intensity at this point? That is Gm over r square, Ig. Any point you take at a distance r, the gravitational field intensity magnitude would be exactly same, anywhere you take. All right. And what would be the direction of force? It would be coming towards it. It will attract the particles. So that's the direction of field line. These are called the field lines. These imaginary lines which we are drawing, those are called the field lines. So basically force exerted on a unit mass is called the gravitational field intensity, right? So actually, if I say that on a unit kg mass, just a second. Yes. On a unit mass, the force exerted is Ig, right? On a unit kg mass, the force exerted is the gravitational field intensity. So what is the force exerted on m kg mass? Just multiply with m. It's that simple. So total force exerted on m kg mass would be m multiplied Ig. Apply that analogy. In 1 rupee, you get 10 books. So how many books you'll get for 10 rupees? 10 multiplied 10. Similarly, on unit kg, the force is Ig. So what is the force on m kg? M multiplied Ig. So this Ig is basically what? Capital F upon m. That is what we call the gravitational field intensity. Now it is a point mass I have taken here. So due to this point mass, the gravitational field intensity would be Gm over r square. Because if you take a unit kg mass particle here, it would be exerting a force of Gm by r square. This is basically called the test mass. This unit kg mass which you are bringing here, on which you are calculating the force to calculate the gravitational field intensity, it is called the test mass. So you bring a unit kg mass, which is just a test mass, and now you calculate a force on it. That force exerted by the capital M on a unit kg mass is called the gravitational field intensity. I hope it's very simple. On a unit kg, the force is Ig, right? Okay. So that is the meaning of gravitational field intensity. So how does it help you now to solve the problems? Suppose you have a capital M mass body. Now what is the gravitational field intensity here at a distance r away? You would simply say that at a distance r away, the gravitational field intensity would be Gm over r square. Now if somebody says, let's say I place 10 kg mass there at this place. If I place 10 kg mass, what will be the force experienced by it? What you have to do, you just multiply this thing with 10 kg. Because that's the force on a unit kg. So for 10 kg, multiply with 10. Similarly, if somebody says, no, I'll keep 1,000 kg mass there. So multiply this thing with 1,000 kg mass. So actually it is like a multiplication factor. The gravitational field intensity. Unit kg, this much. Gm by r square. So for 1,000 kg, just multiply with 1,000. So actually if you see what is happening here, to calculate gravitational field intensity, you divide the force with the mass. Right. So actually it's a force experienced by unit kg mass. So what would be its unit? Newton per kg. Or more specifically, what is Newton's unit? That is kg meter second square. Now kg and kg will get cancelled out. So this is nothing but meters per second square. And that's the unit of acceleration. So gravitational field intensity is what? It's an acceleration. Right. So basically, if I say that the gravitational field intensity is I here, what would be the force experienced by this small m mass particle? So what you will do, force is equal to mass multiplied I. And now you should recall the Newton's second law of motion. Force is equal to ma, mass times acceleration. So this gravitational field intensity is just an acceleration only. right? So whatever you have been calling small g, small g, small g in the previous chapters, that was nothing but the gravitational field intensity. When you calculate this value for the Earth planet, then you get to be value 9.8 meters per second square on the surface, right? Let me just tell you that also here. If you calculate this number, just a second. Yeah. So for Earth planet, if you calculate it on the surface of Earth, because surface Earth is also having some mass. So if Earth is having some mass, it can exert a force on others. So what is the force exerted by Earth on a unit kg mass particle? That is its gravitational field intensity. So Ig. So what would be that number? So G capital M divided by R square. Right? Now what values you will be putting here? I'm not writing small m because small m is 1 kg. I'm calculating the gravitational field intensity on the surface of the Earth. Right. So when I calculate the gravitational field intensity on the surface of the Earth, what answer I'll be getting? So put G is equal to 6.67 multiplied 10 to the power minus 11. You have learned this in the previous chapter. This value you put here. Capital M is the mass of the Earth, which is 6 approximately 10 to the power 24 kg. And small r, now we will take the radius of the Earth. Because from the center of the Earth, if you take the surface, particle is kept here. So this distance would be the radius of the Earth. And that you can take as 6400 kilometer. When you put all these numbers there, you get the answer approximately equal to 9.8 meters per second square. So it's very wonderful that to calculate the gravitational field intensity, it is the 9.8 meter per second square on the surface of the Earth, which you call the small g. So do not get confused. Let me compile what all we have discussed. What is small g? It's a gravity, what we call, right? So gravity is nothing but the gravitational field intensity only. Yes, gravity is nothing but the gravitational field intensity only. And basically, what does gravity refers to? It refers to the force acting per unit mass. That is why you multiply with m every time to calculate the force. If gravity is g, then the force is mg. That's the same thing we are doing here. If the intensity is I, which I'm writing by just a different symbol. So intensity is I, which is the acceleration due to gravity, then the force is mi. It's that simple. So I hope now we are clear with the idea of gravitational field intensity. Now let us check this gravitational field intensity changes or not. Let's say go above the Earth's surface. Will it change? If somebody goes below the Earth's surface, will it change? Let us see this. Just remember what I'm going to do. I'm going to calculate the gravitational field intensity by calculating the force on a unit kg mass. So basically, in the formula of Newton's law of gravitation, I will just put small m as 1. Okay. So now let us begin the variation of small g with height and depth. So first of all, let us see the variation with height. Variation with height, let us see. So let's say the unit kg mass particle we have kept here, and this mass is capital M. Okay. And this is a unit kg mass particle. And what is another name for it? Test mass or test mass. So unit kg mass particle or test mass, which I just bring here to calculate the force on it. And that would be the gravitational field intensity. So what is the gravitational field intensity? Let me write down by the subscript h. What is h? H is the height above the Earth's surface. This height is h. This height is h. Okay. And r is the radius of the Earth. So ultimately, if you calculate the force on this unit kg mass particle due to the capital M, what will be the force? That is the gravitational field intensity, Gm divided by small r square. I'm talking about the Earth right now. In general, you can apply for any other planet also. It would be the same thing. But we can take Earth as almost a spherical body, all right? Though it is not exactly spherical, but we can assume it. So for in general, I'm doing it, but later on, if you put the values for Earth here, like the mass of Earth, radius of Earth, you'll get all the data for Earth here. Okay. Now, what is the value of gravitational field intensity at this place? So it would be gm over r square. Now, what is small r? So small r is this distance from the center of the Earth. Let us apply this gm small r square. How I can write small r? I can write small r as re plus h whole square. Small r is nothing but re plus h whole square. Okay. One more thing. If you have seen the previous slide, how did I calculate the gravitational field intensity on the surface of the Earth? If I have kept on the surface of the Earth, then this distance would be re only, right? So on the surface of the Earth, I can write gravitational field intensity by the symbol G, right? If you're getting confused with this Ig, you can write it as G also. No worries about that. If you want to simply write it as G, just okay. You can write that G also. Just write subscript h so that you understand it is the degree G at a height h above the Earth's surface, not from the center. Height h above the Earth's surface. So what is the gravitational field intensity on the surface of Earth? Just put in place of r, just put re square and unit kg mass. That's it. Now let us do one thing. From the denominator, I am going to take re common. Right? If I take re common, what this will become? Just take re common. It will become 1 plus h by re whole square. Right? So that's the formula for gravitational field intensity at a height h above the Earth's surface. Okay, sorry, I should put square here. I hope you have understood this mathematics. Re square I have taken common. If you are not comfortable with this, what you can do here, you can divide with re and you can multiply the entire thing with re. In the denominator, you divide with re here simply. Just a second, let me do it. If you haven't understood, I'll divide with re, multiply with re. So whatever term I will multiply here inside the brackets re, that I am taking outside as re square. And when you take re by re, it will be 1, and h by re I have written here as it is. Okay, now see one thing. Small g at a height h above the Earth's surface is gm re square multiplied 1 upon 1 plus h by re square. This thing we can write as what? Value of acceleration due to gravity on the surface of the Earth. So 1 plus h by re whole square. Okay. Let's say somebody goes h height above the Earth's surface. So as you increase the value of h, as you go more and more above the Earth's surface, if you're flying and more above the Earth's surface, if you're going, what will happen to gh, the gravity value? Think about it. What will happen if the height increases? So as height increases, see in the numerator, there is a small g. That's a constant value. On the surface of Earth, the value is fixed. It's 9.8. So when we go above the Earth's surface, this h value is going to increase. So when this will increase, this thing will decrease. Because it is the inverse relation. In the denominator it is. So gh is going to decrease as you go more and more above the Earth's surface. So first of all, the simple question have been asked from here also. That why does the gravity decreases as we go above the Earth's surface? That's the reason. Because the h is coming in the denominator. Or simply you can say the distance from the center of the Earth is increasing. Okay. So that's the gravitational field intensity on the surface at the above the surface of Earth at a height h. Now, in the textbook, you will find some simple formulas also written. So how does they come up with those simple formulas? So for that, we need to use some little bit assumptions over here. We have derived the formula small g 1 plus h by re whole square. Okay. So on the surface of Earth, it is 9.8. When you go above the surface of Earth, it will start decreasing. 9, 8, 7, 6, 5, 4, 3, 2, like that. Okay. Now, some simpler formulas are also there after taking the assumption. So for that, something we need to learn new. And this you should remember. In mathematics, you would be doing this in detail, but for here in the grade 9, we have to use it, right? So this thing would be coming for you guys in the grade 11 of maths, something called the binomial expansion. Binomial expansion. So how we will use this binomial expansion here, see. So first of all, let us understand what is binomial expansion. It's a mathematics thing. You don't know it. So first of all, believe that you don't know it, and now you are learning it. So first time you're learning it, so you should remember it so that you can simplify that formula. It says if 1 plus x power n can be anything, n can be 2, n can be 3, n can be 4, n can be 5, like that. So if x is very small, condition is there, if x is very small, then this will become 1 plus nx. If x is a very small quantity, then this will become 1 plus nx. Example. Let us try to understand it. Why we are saying like this? You know the formula of a plus b whole square. So 1 plus x square plus 2x. Now if I'm saying x is very small, what I can do, I can neglect the higher powers of x. The 2 powers of x, the 3 powers of x. So here we can neglect the x square because let's say x is 0.001. So if x is 0.001, then x square would be even less than that, 0.00001, right? So it will become square of it. So that's why this number would become even more smaller when you take square of it. So I can simply write it as approximately 1 plus 2x. And that's what happening here. If 1 plus x power 2, it will become 1 plus 2x. One more example I can show you, then I'll use it here. 1 plus x power 3. So by this formula, I should be able to write it as 1 plus 3x if x is small. How is that possible? So see, a cube plus b cube plus 3a square, which is 1 square into b, plus 3, 1 multiplied x square. Now again, you can see here, I can neglect the higher terms. This can be neglected, this can be neglected. And only we'll keep as 1 plus 3x. And that's what should come out to be. So similarly, higher order powers you neglect here. All right. So that is what the meaning of binomial expansion. Now let us apply this binomial expansion here, but with the condition, because condition says that x should be very, very small. Tell me, can I write it like this? 1 plus h by re power minus 2. Just take it in the numerator. Okay. Now you see, I'm calling this thing as x. If x is very small, and what does it mean? If h by re is very small, re is constant, that's the radius of Earth. So ultimately, it is saying that h is small. If h is small, so what will happen if h is small? You are talking about near the Earth's surface, around 80, 90, 100 kilometers. Even that is more, right? So approximately 60, 70 kilometers you can take near the Earth's surface because radius of Earth is 6,400 kilometers, right? So 6,400 and then kilometers it is. So if you take 50, 60, 70 kilometers, then you can say that it is near the Earth's surface only, right? In the atmosphere of Earth. So here we can see if we are talking about near the Earth's surface, it's a condition, guys. That upper one is a general formula. That's a general formula. It is always valid. But when we take a condition, then when h is very small, now what will happen? This minus 2 will come in the multiplication. So GH will become what? Small g multiplied 1 minus 2h upon RE. Such a simple formula. And here also you can see the h increases, gravity decreases because there is a negative sign now, which will make the decrement in the gravity as height increases. So do remember, this is always valid. And this formula only near the Earth's surface. So that's it. That is about the change in gravity due to the variation in height. When you go above the Earth's surface, the gravity changes. All right. So that's the change in the gravity. All right. Now let us go ahead with one question. So before I come to that question, let us take one. Let us also understand the change in gravity due to depth also. Okay. So let us talk about the change in gravity due to depth. Due to depth. Now, if you are going inside the Earth's surface, so right now you are sitting on the Earth's surface. In the previous case, you were flying, you were going up the Earth's surface. And now I'm saying you are making a tunnel through the Earth and you're going inside that tunnel. Okay, that variation I'm talking about. So let me draw the diagram first of all. Okay, so that's our surface. It doesn't look spherical, but assume it to be a spherical. Okay, and now total mass is m, radius is re, and you want this is the center of the earth, and you want to calculate gravity at this place. At this place, you want to calculate the gravity. Okay. So actually, if you want to calculate the gravity at this place, let's say which is d depth below the earth's surface. Depth is d. All right. So can you calculate what will be this distance, guys? If I call it as small r, what will be the value of small r? Think about it. So depth is d, total this length is re. So if you subtract d from re, what I'll be getting? The small r. Don't get confused, very simple. What I'm saying that d is the depth. You are sitting on the earth surface, you're going d depth below the earth surface. Okay. So small r is the distance from center of the earth. So what is the value of gravity? What is the value of small r? It will be equal to total distance, which is re, minus depth. You'll be getting the remaining one from here to here. Okay. So that's the value of small r. Now, why I'm calculating this? Just wait for a second. You will get it very soon. Okay. Now, suppose if you want to calculate the gravity at this place, let me make an imaginary sphere. It's not a circle, by the way, it's a sphere. We are talking about a planet which is in 3 dimension. Okay, so let me draw an imaginary sphere. So this is the center of the earth, and this imaginary sphere I have drawn, which is having a radius r. I hope you are getting why I'm saying radius r. Exactly, because the d is the depth, and this remaining sphere will be having the radius re minus d, which is nothing but small r only. Now, if we are talking about this sphere, so there are two, basically, what is the purpose of drawing this imaginary sphere? Actually, now you will see that I have divided the entire thing into 2 parts. There is a mass present over here in the outer portion, and there is a mass present in the inner portion, which I am making with red. Everywhere there is a mass. Okay. So we are want to calculate the gravitational field intensity at this place. At this place, we want to calculate the gravitational field intensity at a point P. So if we want to calculate the gravitational field intensity at the point P, what will happen? For that, I have just drawn an imaginary surface. the red color surface and the red color mass and the blue color mass. Mass is everywhere. So I have just, for my imagination, I have divided this into two sections. All right. So now you see one thing here. Suppose now if you want to calculate the gravitational field intensity at the point P, which is at a certain depth D, I can say that that will be due to two different types of masses. The mass which is outside this red color sphere, which I am writing as blue because I have shown it with the blue color. And gravity will be there due to the red color mass. Now the mass color is not red, that is just I have done to make you the clear division that is R I have drawn. And now the gravity will be there due to the blue color mass and the red color mass, which I have shown just for your representation. If you see here carefully, then gravitational field intensity due to this blue color mass would be 0 at this place. Why it would be 0? So see this example. Okay. Here you can see this was the blue color mass. And you wanted to calculate the gravitational field intensity at this place. This is the blue color mass. The red color mass is inside this sphere. So at this place, point P, the gravitational field intensity will be due to P due to two different types of masses. Not different types of masses, just our distinction we have made. This outer mass, which is I have made with the blue color, and the red color mass, which I have made in the red color. Okay. So at this place, the gravitational field intensity due to the blue color mass would be 0. What is the reason? This mass. The reason is because sphere is a symmetric body. We assume that the mass is distributed similarly in a uniform way everywhere throughout the earth. So at this place P, there will be some gravity due to this upper portion. This upper portion, there will be some gravity. And there will be some gravity due to this lower portion. I'm just talking about the outer mass. I'm not talking about the red color mass. Just the outer mass. I'm saying it is 0. Why? Listen me. It's a little bit hard to understand. So try to understand this point here. So at this point here, where we want to calculate the field, I'm saying that due to this black color mass, this point is very close. Right? So distance is very less. But mass is very less also. And due to this blue color mass, which is a little bit far away, so distance is more, but mass is also more. Now, gravitational field intensity is basically having dependence upon mass divided by R. Right? How much is the mass? If you see the general formula of gravitational field intensity, it's the gm by r square due to a point mass. So due to this upper portion, the distance is less. Distance is less. So gravity should be more. But at the same time, mass is also less, which will make the gravity less. Do not get confused. R is less, which means the gravity is high. But capital M is also less, which means the gravity is low. Similarly, for this portion, the distance is more. Distance is more, which will make the gravity value to be less. And the mass is also more, which will make the gravity value to be a little bit high. So one factor is trying to increase the gravity, one factor is trying to decrease the gravity at this point. So due to this outer portion, this mass will be attracting like this, and this mass will be attracting like this, because gravitational field is attractive in the nature. So this point will be attracted by the same forces from both the sides, and which will cancel out both the gravity. Right? So I was just talking about the blue color portion, and hence the field will be 0. So only and only the field will be there due to the gravitational field intensity of red color mass. Alright, so at this place, always remember the gravitational field intensity at this point will be due to the inner sphere only. the outer sphere, the gravitational field intensity will be 0. Now, what should I write here? So it is like simple. Red color sphere, and radius is how much? Small r, not the capital R now, small r, and you want to calculate field here. So what we should mention? G m prime divided by r square. Why did I say m prime? Because listen me, now I should take only this much mass, the red color portion. I should not take the outer mass. Outer mass is giving the zero influence of the gravity at that place, because upper and lower portion is cancelling out. This portion and this portion is cancelling out their gravity. So at this point, the gravity will be there because of the inner portion. So we should only write the mass of the inner portion. So when I write the mass of the inner portion, which will be m prime. Okay, we know the value of small r, by the way. Now, how to write down the value of m prime? It's very simple. Again, a unitary method. Total volume of the earth is 4 by 3 pi r e cube. In the total volume, the mass is capital M. So in unit volume, what is the mass? M up over 4 by 3 pi r e cube. That's the density, basically, mass upon volume. Total volume 4 by 3 pi r e cube, mass is capital M. In a unit volume, mass is capital M upon this. So what is the mass present in this small r sphere radius? So in the 4 by 3 pi r cube volume, pi r e cube, the total mass is, in the total mass is capital M. In unit volume, the total mass is this. So what is the mass in this much volume? So just multiply this with 4 by 3 pi small r cube. 4 by 3 pi, 4 by 3 pi will get cancelled out. And what you will be getting? The m prime as capital M small r cube divided by capital R e cube. So I hope you understood how did I calculate the mass? Unitary method. In unit volume, this is the mass. So what is the mass in the 4 by 3 pi small r cube volume? Just multiply with that. Okay. Now once we get this, now I am going to put these numbers here. So total gravity at depth d will be equal to G m dash value is capital M small r cube divided by r e cube multiplied r square, because gm by r square was g by r square was there, so g by r square, and capital M dash is equal to capital M r cube over r e cube. Now you can see r square will get cancelled out by r cube here, and you will be remaining with g m small r upon r e cube. All right. Okay. So that's the value of gravitational field intensity. Now let me just go to the next part here. So here we can see the gravitational field intensity has become this much. Okay, let me write here now. If it is becoming confusing there. So small g is equal to gm divided by r e cube multiplied, see, small r upon r e cube. So that's it. Now what was the small r e? Small r e was nothing but the r e minus d. So gd, gm by small r e cube, and small r is nothing but r e minus d. Now see one thing. Can I write it as gm by r e square? And one re I am taking in the denominator of this thing. Yes, we can write it. Re cube I can write as re square multiplied re. Now what is this thing again? Small g. So this gd will become what? Small g. This re will get divided. So 1 minus d by re. So that's another formula you have got for gravitational field intensity at a depth d below. So actually you see here, in deriving this entire formula, I did not use any approximation. So this is the general formula. you should remember it directly as it is. G multiplied 1 minus d over Re, where small g is the gravitational field intensity on the surface of Earth. But if I talk about this formula for the height, which came out to be like this after taking the approximation that near the Earth's surface. But here, this is the general formula. So this formula you should remember, this you should remember, and this also you should remember. All the three things you should remember, because we are going to use them directly in the questions. How? Let me show you this. So this is the question from the NEET exam. If you have heard of it, the exam to be for admission into medical institutes, you have to write down the NEET exam. So this question was asked there. So you can do it now in the grade 9 itself. Acceleration due to gravity at a height 1 kilometer above the Earth is same as at a depth d below. Okay. So what is the formula for height? Small g, 1 minus 2h over Re. At a depth, formula is small g multiplied 1 minus d over Re. Right? Now they are saying at a height 1 kilometer above. See, that's why I've used the approximated formula for height, because it's a 1 kilometer above the Earth's surface, which is very, very close. So now let me put the numbers, and they are saying that these two are same. This GH and GD are same. So let me just equate them. So small g, 1 minus H value is 1 kilometer divided by Re is equal to small g, 1 minus depth we have to calculate, Re. Small g will get cancelled out. So you will be remaining with 1 minus 2 over Re is equal to 1 minus d over Re. Just check if I'm making any calculation mistake here. Now 1 will get cancelled out, then minus and minus will get cancelled out, and you will get 2 by Re is equal to d by Re, which will again cancel out the Re term. So from there you'll get d is equal to 2 kilometers, because I used units as kilometer here. H I put in terms of kilometer only. So that's how we get the answer for what? That's how we get the answer for small d. That's so if you go 1 kilometer above the Earth's surface, and if you go 2 kilometer below the Earth's surface, the gravity would be same. Right? Achha, one more thing we didn't, if you have noticed here or not, I'm not sure. This is the formula for gravity due to depth. When this d will increase, what will happen to gravity? It will decrease, because there is a negative sign. So as you go down the Earth's surface, below the Earth's surface, if you dig a tunnel and if you go inside that tunnel, the gravity will keep decreasing. So on the surface of Earth, it is 9.8. If you go above the Earth's surface, it decreases. If you go below the Earth's surface, it decreases. So where is the maximum? On the surface. So the place where you are living on the Earth, that is the surface of the Earth, and the gravity is maximum there. If you go below, you will feel lightweight. If you go above, you'll feel lightweight, because the net weight would be less. Do not get confused. In the next lecture, we're going to talk about the weight concept only. All right. So that is what the meaning of gravity, right? Okay. Let's take one more question. Imagine a new planet having the density same as that of Earth. So some new planet. Let us call it by some prime. Okay. So density of the new planet is same as density of Earth, but it is 3 times bigger than the size. So radius of the new planet is 3 times the radius of the Earth. If the acceleration due to gravity on the surface of Earth is small g, right? Then find out, and that on the surface of new planet is g dash, g prime, then what would be the relation between them? Means g dash and g. What's the relation among them? This is also a NEET question. In the medical exam, this have been asked previous year. I don't remember the year exactly. So g dash and g, that's the relation they are asking from us. Okay. So this d is the density. Do not get confused with the depth here. So on the surface, their density, their gravity relation they want to calculate. On the surface of Earth, we can write G as capital G, capital M over radius of Earth square. What is mass? Density is mass over volume. So I can write mass as density multiplied volume. So I can write this thing as density multiplied volume divided by Re square. Now what is volume? 4 by 3 pi Re cube divided by Re square. Now this will get cancelled out, Re square. So ultimately you will get G is equal to G small d 4 by 3 pi Re. Again, I am repeating, do not get confused small d with depth here. That small d is representing the density. Okay. Similarly, for the new planet, what you can say, guys? For the newly discovered planet, you can say G prime will be equal to what? By the same thing. G, its density, 4 by 3 pi, and radius of that new planet, R prime. Okay. Because the formula is same, just the naming would change. And now they are saying what is the relation between them. So let us do one thing. Let us divide G prime and G. So when I do that, G prime, we can write here. G prime divided by G. What I'll be getting? So just check. G prime is nothing but GD prime 4 by 3 pi R prime divided by small g is GD 4 by 3 pi RE. 4 by 3 pi capital G will get cancelled out, and D prime and D, density of Earth, that is also same. So this will also get cancelled out. And R prime is nothing but 3 times that of radius of Earth. So what I'll be getting? G prime upon G. R prime is 3 times the radius of Earth. Just check if I have made any calculation mistake. Okay. So G prime over G is 3, which will make G prime equal to 3G. And that's the relation among them. And that was one of the option in the exam. Okay. So that's how we will be solving the questions which are related to the acceleration due to gravity here. All right. Next. Last concept. Now it is very easy for you guys. So earlier what used to happen in the chapter number 1, motion in 1 dimension, motion in 2 dimension, Newton's laws of motion. Always we have been taking small g as 9.8 meters per second square, close to the Earth's surface. Because we have been talking about the heights in meters, 100 meters, 200 meters, 1 kilometer, 2 kilometers, not more than that. So you can neglect this variation in gravity, right? So when you drop a particle from a certain height, right? When you drop a particle from a certain height, it will fall down like this. That is called the free fall motion, right? It is under the influence of gravity only. That is called the free fall motion. Okay. So that's how we understand the value of acceleration due to gravity. Okay. Now the thing is, we have finished the gravity concept in this particular part. So what did we learn today? First of all, we understood what is the concept of gravity and what does it says, and we also understood what does it mean. All right. And now we also know that once we understand the concept of gravity, then simply we can use it if you want to find out the weight of a body at any height h above the Earth's surface, if you go d below the Earth's surface. So in that regard, we will be using it. So this particular session would be very helpful if you will be learning how to calculate the apparent weight of body when you go h height above the Earth's surface, when you go d depth below the Earth's surface, for that kind of stuff. Okay. So I hope you have got this lecture. So just remember a few key points. I am reminding them now. First of all, gravity decreases as you go above. Formula is 1 minus 2h by Re multiplied g. But that's the approximated formula when near the Earth's surface. In general, formula is small g divided by 1 plus h by Re whole square. When you go d depth below the Earth's surface, this d is the depth below the Earth's surface. Again, the formula is small g multiplied 1 minus d over Re. After this, the next part is what is the maximum value of gravity on the surface? Then it is on the Earth surface only, which is equal to 9.8 meters per second square. Okay. And then in the end, we talked about the free fall motion, means falling under the gravity. So if you go down, your velocity would increase. So here, as you can see, this stone is starting with the 10 meter per second, and as it goes down, the velocity keeps increasing 10, 20, 30, like that. If it starts with 0, the velocity will keep increasing 20, 30 because Earth is attracting it. Similarly here also. All right, so that's the overall idea about this session. Oh, I hope you have understood everything. If you get any confusion, any question if you have, just put it on PDF. I hope you enjoyed the lecture. And now you do some numericals also over it. You will find some numericals in the module, in the study material, in your reference book, in the NCERT textbook, right? I believe you would be able to solve them now. Even the grade 11 question you will be able to solve now. It's that level curriculum like we have covered today in the class. Okay, so that's all for today. Thank you so much, guys. Enjoy.